Ad Astra is our mantra. Ad Astra to the stars. Ad Astra, it's who we are.
Welcome to Around Space. I'm Kent Miller. Today we're going to be talking about Gaia, an ambitious satellite program by the European Space Agency. It's supposed to map over 1 billion stars. Many of them will get the full velocity components of them. I'm delighted to have with us Dr. Bradford Baer, an astronomer and optical engineer. In 1992, he got his Bachelor of Arts in Astronomy from Williams College in Massachusetts. In 2000, he got his PhD in Astrophysics from Caltech. From then until 2003, he worked at the McDonald Observatory in Texas. And from 2003 to 2007, he worked at the U.S. Naval Observatory here in Washington, D.C. Since then, he's branched off into the private sector, bringing astronomical spectroscopy down to Earth. Welcome back to this table.
Thanks, Kent. It's always great to be here.
So tell us about Gaia.
Gaia is the next generation of astrometry, if you will. It's the follow-on to another European Space Agency mission that we talked about, I think, about 3 years ago on this show, called Hipparcos, which measured the positions of stars in our local vicinity in the Milky Way galaxy very accurately. And a lot of really good science has been done based on that data set from Hipparcos, but you can always do better. And just about the time we had that show, they launched this follow-on mission, Gaia, which not only is going to be measuring those stars more accurately, but also looking at the spectra of these stars in order to see how they're moving and what they're made of. And this is really going to be one of the most comprehensive and complete censuses of the Milky Way that we've seen to date.
Mm-hmm. And astrometry means the measurement of the stars. So we're measuring what?
Fundamentally, just where they are, very accurately, where they appear on the celestial sphere, where their positions as seen from Earth.
Mm-hmm.
And
with greater precision than ever.
In this case, with exceptionally high precision, and that lets you do a lot of, derive a lot of useful information about what they're doing and where they are in the Milky Way. Mm-hmm. So most of our viewers, I think, are probably familiar with the idea of parallax. As the Earth goes around the Sun, we're looking at the universe from a slightly different angle, and stars that are close to us will appear to shift back and forth or move in little circles because they are closer to us than the background stars.
So we can get the distance of the star.
Right. The farther away it is, the less that shift, and you can, knowing how big the Earth's orbit is, you can derive the distance to those stars very accurately.
How about the motion of the stars?
And so similarly, since we are in the Milky Way, cruising along at a great clip, and all the other stars are generally going in the same direction, but some of them faster, some of them slower, you will notice that some stars will, most of them in fact, will show what's called proper motion. They will, year by year by year, in addition to this little circular motion, they will be drifting or moving in one direction or another. And knowing how far away they are and how fast they seem to be moving sideways, you can calculate how fast they actually are moving in the galaxy, what sort of orbit they're on around the center of the galaxy.
Okay. Now, when I was in college, I heard about Barnard's star, which is one that moves exceptionally fast.
Right.
Its proper motion is quite exceptional.
Partly because it's close to us, but partly also because it is doing its own thing. It's perhaps part of a different population within the Milky Way galaxy, formed somewhere else, and it got captured, and so it's on a different orbit than the vast majority of stars that we see in the sky.
Okay. But this will be the first time they'll be measuring millions of stars in all of their components.
Right, or as you mentioned, even up into the billions. So Hipparcos did measure hundreds of thousands, if not millions of stars with reasonably good accuracy. But with Gaia, not only are they doing 10 to 15 times better in terms of that accuracy, they are also adding a spectroscopic component. And I'm a big fan of spectroscopy. It's my line of work. So looking at the detailed color patterns, breaking the light from each of these stars into the rainbow, and that lets you measure the velocity towards us or away from us, as well as getting a pretty good handle on what the star is made of and whether it's a dwarf or a giant. So the combination of the really high precision astrometry plus the spectroscopy is going to let us not only figure out where these stars are in the galaxy and what direction they're moving in all three spatial dimensions, but we'll be able to figure out if they, where they came from, what their formation history is, and whether they are old stars or middle-aged or recently formed, and if they have any other special properties.
Right. I understand if the color of the star is reddened, that would suggest there's dust in between, and so we might be able to map out the dust.
That's another key component of understanding our Milky Way as a whole. It's not just the stars. There are, as you say, there's a lot of interstellar material, dust and gas, and using these stars as a backlight, as you will. The light coming from the star, some of it will get absorbed, and yes, from the color and also from specific features that show up in the spectra, you can say, oh, there's a molecular cloud, otherwise invisible, that's blocking some of the light from this star.
Right. Now, there was a recent announcement.
Yes.
This is 2016.
Right now, in late 2016, the ESA, the European Space Agency, announced the first data release of 1.1 billion stars that Gaia had observed and had gotten at least some preliminary data on. Now, this will be the first of many, probably dozens of data releases over the coming years, but they wanted to get the first batch out there. And it is being released to all astronomers everywhere, and anyone else who wants to go to the website and download these gigabytes and gigabytes of it's not pretty pictures, although they do have some pretty pictures on the website, but what's really of interest is just numbers and numbers and numbers.
Yeah, a huge spreadsheet, basically.
Huge spreadsheet, but analyzing that spreadsheet in different ways will reveal all sorts of interesting things about our galaxy.
Yeah, amazing. So when did this launch?
Late 2013, I believe. They sent it up into orbit on a European rocket, and it went up to the Earth-Sun L2 point.
I think it might have been a Russian rocket.
Oh, okay, my bad.
But you're right, it would launch from Guyana, which is the French,
former French colony.
Yeah.
So yeah, they sent it up into a particular orbit that is very gravitationally stable, and far enough away from the Earth that they would be able to get a pretty good view in all directions. And this satellite has a very big camera, which we'll talk about shortly, but it is set to deliberately spin at a certain rate and be able to look in multiple directions at once, gradually mapping out the entirety of the celestial sphere, being able to look in all directions eventually.
I think it's like 5 times a year or something like that, or no more than that maybe.
Well, it is as the Earth goes around the Sun, it's mostly looking away from the Earth-Sun direction to get the clearest view. But so it's essentially a fairly narrow strip that it can see at once, but it's just going around and around and around and cutting the entire sky up into stripes that it will then revisit over and over and over again. I think each star on average, is going to be reobserved 70 times over the 5-year course of the
70
mission.
or 80 times over 5 years.
Yes.
Yeah. So that'll be a huge data set when they get done.
Gigs and gigs, but lots of interesting stuff to be found, and different astronomers are going to be looking for different sorts of things in this data set. So it's going and probably even discover some things that no one's even thought of when the mission was first conceived and proposed.
Now, when you propose a mission, you have to think of, you have certain customers, people who want to use the data to find certain kinds of science. So and that somehow gets distilled down into performance targets or some kind of goals.
Right.
What kind of performance targets were designed into this?
Well, the much more accurate positional accuracy, the astrometry that we talked about earlier. Hipparcos, I think, was able to measure the brightest stars down to an accuracy of about 100 milliarc seconds, where an arc second is a 60th of a arc minute, and an arc minute is a 60th of a degree. So we're talking about very, very tiny angles. I don't remember exactly. It's something like the width of a human hair a mile away, or something even more impressive. But essentially, being able to measure those positions, those relative angles between stars, with 10 to 15 times better accuracy than Hipparcos had done before. But then also getting the radial velocity, the motion of the star towards us or away from us, to about a half a kilometer per second, which is, that's pretty fast by Earth standards, but in terms of the speeds that these stars are whirling around in the galaxy, that's pretty accurate, and that lets us tell where they're coming from and what direction they're headed.
So that'll allow us to map the flow of stars,
right,
at least in our neighborhood.
Right, and a pretty good section of our neighborhood. The sort of sphere centered on Earth, within which we'll be able to measure stars, extends nearly all the way to the center of the galaxy, getting some of the bulge that's at the yolk of the fried egg that's the Milky Way galaxy, as well as our local spiral arm and further out in the anti-center direction.
Right.
So yeah, a billion stars is a pretty good. It's still only a percent or so of the total number of stars in our Milky Way, but we assume that those are representative of all the others that we can't see, that are further away.
Right. Now I understand from the way it gradually maps, it kind of looks like a ball of yarn, how it
gradually
wound in all
winding
different
or
ways.
unwinding it. Yeah. Exactly, that's a good analogy.
But it'll cover even things that are outside of the galactic plane.
Right, looking galactic north and galactic south, where there are interesting other components of the Milky Way, the so-called halo, and that's where I think some of the most interesting stuff is going to come in. The Magellanic Clouds, the two satellite galaxies of the Milky Way, are thought by many astronomers to be the leftovers, perhaps, from the formation of the Milky Way, that instead of just congealing or coagulating out of a huge ball of gas, that galaxies like our Milky Way are formed from a lot of smaller galaxies, dwarf galaxies as they're called.
Somehow coalesced.
Right, that ran into each other and were held together by, or drawn together by their own gravity. And it's certainly not obvious, looking at the Milky Way today, that there are blocks or chunks or individual components that formed it. But one of the main goals of Gaia is to identify these groups of stars that all showed up to the party together.
Right.
Because they're all still, even after many orbits, they're all still moving together in the same general direction, and just as importantly, they have the same chemical composition, the same mixture of all the heavier elements besides hydrogen and helium.
Metallicity.
The metallicity and the particular patterns of those those metals, the iron, the calcium, and other elements from the periodic table. So if you can teach your computer to go looking through this enormous spreadsheet and say, find all of the stars within this range of metallicity in this part of the galaxy, all moving in this direction, you may be able to see the remnants of these building blocks, these dwarf galaxies that all came together 10 billion years ago or more to form the Milky Way. So that, I think, is the main rationale for the whole Gaia mission, but certainly not the only one.
Now, I understand, this surprised me when I learned it, is that it'll also pick up asteroids.
Yes, I mean, it's going to be looking in all directions, and including the ecliptic, the plane of our solar system. And so anything that happens to be passing through the field of view of its camera, like an asteroid, they expect to be rediscovering many of the known asteroids and probably discovering a whole lot of new ones, as well as out in the Kuiper Belt, those dwarf planets and comet nuclei and such. Anything that's reflecting a little bit of light is likely to get picked up and will appear very differently, because those nearby objects are going to appear to be moving a lot more quickly. So they will either, from one picture to the next, it'll move by a big jump, or
right.
in some cases even be kind of a streak.
A streak, yeah, that's right.
So all the solar system planetary astronomers, planetary scientists, I'm sure are going to be plumbing through that data set, looking for the nearby stuff. A whole lot of quasars in the distant universe are likely to show up. And even the people hunting for planets around other stars are interested, because there are several different ways, as you know, to detect a planet orbiting another star. In some cases, you look at the spectrum of that star, and it gets redshifted, blue shifted, redshifted, blue shifted as that little gravitational do-si-do happens. In other cases, the Kepler mission is looking for the shadow, the eclipse of the planet going in front of the star. But what Gaia is expected to be able to do is to see the side-to-side wobble of a star due to the planet tugging on it ever so slightly with its gravity. And that's very complementary to the radial velocity measurement of moving towards or away from us. So
each star is going to be looked at 70 or 80 times. If we see a couple of them which are dimmer or brighter, or red shifted or blue shifted, that's a lot of useful information.
Exactly. They'll be, I think, a good 30 or 40 or even 50 years, people are going to be digging into this data set and turning up all sorts of new stuff. So this recent announcement was not, hey, we discovered something. It was, hey, the instrument, the mission is working, and here's the first batch of data that came out of it, and more to come. So it's sort of an announcement of the opening of the floodgates.
Yeah.
And there'll be all of these sorts of studies that we just discussed will certainly be done, but I expect there'll also be something completely unexpected. Some clever graduate student somewhere will dig into the data with a new algorithm and announce something that no one ever even imagined is lurking out there or going on in our galaxy.
Now, one of the interesting things is variable stars.
Right.
For example, Cepheid variables are used as a standard candle. We assume there's a relationship between the luminosity and its period.
Right, it gets brighter and dimmer, and the overall brighter it is, that relates to how long it takes to go through a cycle. Right.
And for that reason, we can get an idea of how far galaxies are, because these Cepheid variables are so bright. There's the hope that this mission, Gaia, will get very accurate distance information to the local or our nearest variables.
Yes.
And so tighten up our understanding of
right,
that.
the so-called distance ladder.
Yeah.
It's a chain of reasoning that astronomers use to figure out how far away the most distant things are based on more nearby objects. And it all ties back to figuring out through astrometry and this parallax effect, how far away are the, I don't know, 20 or 30 or 50 or 100 nearest Cepheid variables, and that provides a calibration that then gets applied for, just as you said, figuring out, oh, we see a Cepheid variable, it's got a very characteristic shape of brighter and dimmer, and you can, if you see that happening in the Andromeda galaxy, you can back calculate, you can figure out how far away that star must be to appear as dim as it does. Mm-hmm. So yes, this mission is going to have very far-reaching implications for pretty much all of astronomy.
Now I understand this mission will be able to see stars down to magnitude 20,
right,
which is rather dim.
Yes.
And maybe even further than that, which means they'll be able to see the brightest stars in Andromeda and other local galaxies.
I believe in the recent press release, or one of the recent announcements from ESA, they had already had a look at some of the stars in the Magellanic cluster, the large and small clouds, and that's sort of a stepping stone to Andromeda. So yeah, I mean, Andromeda, even as our nearest large galaxy neighbor, is still quite a ways away. So those stars will be dimmer, but some of them, at least, I think, within that range. And not Hipparcos, Gaia certainly can see dimmer stars than that, just won't be able to measure their positions as accurately. The fainter they are, the fewer photons you have, the more uncertainty or more static there is in making that very precise measurement.
Mm-hmm. Let's talk a little bit about dust.
Yes.
And these molecular clouds. I understand this is how, when we get a big clump of dust, and perhaps you need a shock wave to travel through it, then it might collapse and create new stars. So
right.
There's
turn into a star-forming region.
Right. So let's talk a little bit about dust and why we want to map that out.
Part of it, as you say, is because that's where the next generation of stars may come from. And depending on how enriched that dust is, how many of those heavier metals that we talked about earlier are present in the dust, that will have a big impact on how the stars form and perhaps how planets then form around those stars.
Well, this is interesting because if there's metals in the dust, well, that metal had to come from a supernova, right? Because as we understand it, metals weren't created in the Big Bang.
Correct.
They have to have been created in a star and then ejected somehow.
Either in a supernova or sometimes more gently or gradually in
the evaporation.
The evaporation, a red giant gradually boiling away its outer layers, or other such stellar death throes. But yes, those processed materials from the heart of the star get dredged up and ejected and then incorporated into the following generations of stars.
Interesting.
And those clouds, the molecular clouds and the interstellar dust also are telling us a lot, potentially, about the dynamics of the galaxy as a whole. So yeah, mapping out those clouds is important in that respect, but also because although they rarely block our view of other stars completely, they can block some of the light from those stars. And
I think the word is extinction.
Extinction, right. And reddening. Much like the sunset, especially after a volcanic eruption when there's a lot of dust and particulates in the Earth's atmosphere.
Yeah, we get a few years of red sunsets.
Especially red sunsets. And the same sort of thing happens with just looking at a star. It may appear redder than it truly is because we're looking through some amount of dust, and that can be misleading. You may think, oh, it's a red giant, when actually it's a yellow supergiant. So mapping out one of the most cited papers in all of astronomy, that is, other people's scholarly papers refer to it and use its information, is a map of dust all around the Milky Way. And it's not headline news, but it is one of those fundamental
Yes.
publications that everyone refers to in order to make sure that their analyses and their observations aren't being contaminated or getting misleading results.
All right. I understand dark matter is a big topic. Now, we won't see this with the telescopes, but we might be able to see the effects of it in the motion of stars.
Yes, and that's how dark matter was first discovered, although it's been discovered insofar as that we know it's out there, but there's still an awful lot of puzzlement as to what it actually consists of. But there's, in addition to all of the stars and all of these molecular clouds and all of the planets, and there's something else out there that we're pretty sure isn't even normal matter. It's not the atoms and molecules that we're familiar with. It's got mass, it's got gravity. We see it, quote unquote, because of its gravitational effect on the luminous matter. Mm-hmm. But that's probably going to be another great spin-off or result from this final Gaia map. As we see all these stars whirling around and getting a sense of their trajectories, mm-hmm. we'll have a better sense of where that invisible matter is. Right. Tugging on it, and we know it's here in our Milky Way as well as pretty much every other galaxy.
There seems to be several times as much mass that's dark compared to what's luminous. So the flow of these stars might help us understand where it is.
Where it is, how it's distributed. Is it spread out uniformly, or is it a lot of little clumps? Mm-hmm. So yes, yet another potential result of the Gaia data set once it's completed.
Okay. Well, thank you so much.
Thank you, Ken.
Thank you. And thank you for joining us here at Around Space. That was Dr. Bradford Baer, astronomer and optical engineer. Look forward to seeing you next time.